In problem number 2, we start with a target equation again. 2 carbon dioxides plus water react to form C2H2 and 5 halves O2. This notation, 5 halves for O2, is pretty common. You're going to see things like this in Hess law problems, but don't worry about it. It's just another coefficient, and we can see that it all works out for the balancing. Makes it a little bit easier because we don't have to have a lot of coefficients in front of other things. So I need to find the enthalpy of my target reaction. And I'm given these through. Reaction number 1 shows C2H2 plus hydrogen gas making C2H6. That's an exothermic reaction with negative 94.5 kilojoules. I'm given this reaction that H2O in the gas phase can be split into hydrogen gas and oxygen gas. There's that notation again, 1/2 oxygen gas. And that is an endothermic reaction, absorbing 71 kilojoules. And finally, this reaction, C2H6 plus 7/2 oxygen, making carbon dioxide and water. That's a combustion reaction. Not surprisingly, combustion is exothermic, 283 kilojoules. So my first step was to make sure that things were on the right side of the arrow. So I lined up my arrows again so I could see I need to have carbon dioxide gas on the left side of my arrow. And I don't. It's on the right side of my arrow. Right? I need to have H2O gas on the left side of my arrow. And I do. Here it is on the left side. It's also over here on the right side. I need to have C2H2 on the right side. Here it is on the left side, so equation 1 gets flipped. So far I've determined that we're going to have to flip equation number 3, and now we have to flip equation number 1. And the last thing I can look for is oxygen. I need to have O2 on the right side of the arrow. And I do, plus I already said I was going to flip this one, so I'm going to have it on the right side of the arrow. So if I flip the first one so that I've got my C2H2 now on the right side of the arrow, I flip it all across and I change the sign. Delta H is now positive. I flip my last one, that I had to flip this one also to get my CO2 on the proper side. So it is, this is flipped over, and I've also changed the sign of delta H. Now, one of the things that I needed to look for was that things had to disappear that I didn't want, right? So C2H6 is not in my target equation anywhere. So right now, C2H6, because of the flip, is on the left side, and it's on the right side. So that's great. It's going to cancel just like I want it to. That last equation, I wonder, here I have this H2 gas. I don't have any H2 up here at all. So if I've got H2 gas here on the right side, and I need it on the right side, rather I needed to flip this equation to put the C2H2 on the right side, I'm going to need to flip equation number 2 also so that the H2 ends up on the left side and it will cancel. All right. So at this point, I've looked at it and I've determined I'm going to have to flip every one of these equations. All right, no problem. They're all flipped. I've changed all their signs of delta H, and I have made sure, for example, that my C2H6 over here and my C2H6 over here are going to cancel because they do not exist in my equation. Now, I also said I wanted these hydrogens to cancel. So in order for these hydrogens to cancel, I need them on both sides, and I have that, but there's two of them on the right side and only one of them on the left side. So to get the hydrogens to vanish, I need to take advantage of the fact that enthalpies are extrinsic, and I can simply multiply this entire bottom equation, including its enthalpy, times 2. So if I go through and I double everything, so now I have 2 H2s, and that's enough to make this cancel. I have 2 halves oxygen and 2 waters, and I have twice as much, still the same sign, but twice as much energy involved. So to neaten this up, because now I'm not using this equation at all. Now this equation has been replaced by the one below it. So if I neaten this up, here I have my 3 equations, this one, the bottom one being doubled, and I can add them together. Now the first time we did it, we added it together and then I showed you the canceling. But that can get pretty long. You can see there are 5 different chemicals just on the reactant side, and another 5 different chemicals on the product side. And a lot of them are going to cancel out. So we can cancel out right here and now. We can simply say, look, C2H6, here it is on the left side, here it is on the right side, it's gone. 2H2, there it is on the right side, here it is on the left side, it's gone. 2 waters, 3 waters. These 2 disappear, and 2 of those disappear. There's now just 1 water left. And then 2 O2s and 7, or rather I should say 2 halves and 7 halves. These completely disappear. The 7 turns into a 5. Right. So now, what do I have left on my reactant side? I have 2 CO2s. That matches. I have 1 H2O. That matches. Everything else is gone. On my reactant, on my product side, I've got C2H2. That matches. And I have 5 halves O2. That matches. So I can add this all together now. I've got my target equation, and by adding together all of these numbers, I end up with the enthalpy for my target equation is plus 235.1 kilojoules.